All right, everyone. Today I want to explore the concepts of probability of default, loss given default, and exposure at default. So I've been in the finance sector pretty much my entire career. I worked on Wall Street about 2 decades, finished my MBA in finance back in 2003, and I've been pretty close to this stuff ever since. So I've done this in the past. I've seen the good, the bad, the in between. So definitely see some ugly stuff out there. So I wanted to put this together to potentially fill in a couple knowledge gaps. I haven't done this in a little while, but also share my findings with you guys and make sure that you're doing it pretty much on point with where it should be. I've seen all kinds of things, and some of these things, by the way, are a little bit arbitrary. There's a little wiggle room with how you can do this stuff. There are certain expectations and certain constraints, and there's guardrails that you have to work within, right? You can't just do whatever you want, but some of these things are kind of flexible too. So take a look at that. Like this is not just done one absolute specific way. And at different banks, there's different policies and procedures. There's different focuses. There's different expectations, right? And there's ways to embellish the data. You can look at current economic data. We're in a high interest rate environment right now. It's late 2024 when I'm recording this video, specifically November 6th, 2024. So interest rates are pretty high. It used to be low several years ago before COVID. COVID killed all that. Several years now, I don't know where we're going to be. But anyways, in economic indicators might be something that you want to add to your data set to embellish the results. We just had an election yesterday. So if you had some political data that could be relevant to helping you understand the probability of default, loss given default, exposure at default, that might be helpful too. There's financial factors, certainly the risk of the clients that you're lending money to. That's what we're going to focus on in the example. But there's other data points that you can add into your analysis to make it more robust, more refined, more, more elegant. But right now we're just going to focus on the data set that we have. I found this online. I'll share the URL resource at the end of this Jupyter Notebook. I've referenced it here. This is where it's coming from. I don't want to jump around a whole lot, but basically this is source data. I'll include this with my code when I download it. So it's credit data, and the CSV file is right here. So you can go ahead and grab that and then do this analysis yourself. Right? And the best way to learn all this stuff is to copy paste the code, run it, understand the results, interpret what's happening here, and then go ahead and make small modifications or improvements to the code. Right, you can do what you want. That's why I like to share my Jupyter notebooks. It's very interactive. And then if you have some customization that you need to do, by all means do it. Right, like these all these videos that I put together, I've got I think close to 110 now. I try to make it generic, applicable, and relevant. But your specific case might be slightly different than mine. So by all means, make the modifications that you need to make this thing work for your specific use case, right? So let me go ahead and import the data. I'll click on the cell, hit Control Enter to run it, and we can see the looking at data types, summing any potential nulls. Are there nulls over here or nans, right? I'm printing the shape of the data frame and then displaying the head of the data frame so we can get a basic understanding, understanding of what this looks like. So we go down here. Okay, there's the columns, and this is what the data looks like. So there are some nulls in here, and let me see oh yeah, here you can see all the nulls right here. So nan, 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 and nan. So one thing I want to do is fill in these nans. There's a few ways to do this. You can fill forward, fill backward, right? So the last use number could be used for the first missing value. You could take the last missing value and fill down. You could take the mean, the mode. There's a bunch of ways to fill in nans so you have a complete data set. I like this method right here, KNN imputer. So we can actually impute missing values using a machine learning technique, K nearest neighbors. So I'm looking at the 5 closest neighbors, and this is basically like a clustering type of type of logic here, and I have a couple videos that describe how clustering works. I'm not going to get too into it in this video because that's kind of going off topic a bit, but we're going to use the KNN methodology to impute the missing data points, so we have a complete set of data to work with, right? So I'm going to run the cell, control enter to run it, and then again we're going to look at all the is and a. We're going to sum those up. There should be 0 at this point because we are imputing those missing values using this technique right here. Okay, and then we should have a fairly comprehensive and 100% complete data set that we can start working on. This is taking a little bit of time. That's okay. I'd rather take some time and do it right and get these missing data points filled in rather than try to train these machine learning algorithms on incomplete data. And by the way, some ML algos will compute, even if the data is missing, they'll still converge at the end and they'll do what they're supposed to. Some of these will not. You have to have a full, complete data set. If you have even one single NaN, for some algorithms, it just throws an error, right? It just doesn't understand it, can't comprehend, so you have to fill in these missing data points in some cases. So I'm looking at all zeros here. That's good. I think we have mission accomplished, and everything that was NA above, or NaN, sorry, NaN, annual income joint, NaN. Now we have a bunch of NaNs there. Now these are filled in. So I think we're in good shape. So at this point, I want to look at interquartile ranges. You can Google this. This is a way to look for any kind of extreme outlier or any of these columns over here. I want to understand if they have a lot of outliers or if they're mostly homogeneous and mostly similar, right? If you have some extreme outliers, you can have like 18 over here, 5 here, and then maybe 10,000. If there's a debt to income of 10,000, I want to know about that, right? Because that entity or the individual, I guess this is loan data for individuals. So if this individual has a debt to income of 10,000, I'm definitely not loaning to that guy, right? He's got too much debt. He probably has 20 plus loans right now, and that's high risk, right? I'm not going to loan to that guy. So I'm looking at interquartile ranges just to look for what is mostly similar in all these columns. Is the data pretty tight and compacted, or is it just scattered all over the place, right? So that's what the interquartile range is doing for us. We're looking at the lower quartile here, that's Q1, the upper quartile here, which is Q3, and we're going to take a standard deviation of 1.5 to find the lower bound and the upper bound. So we have the data frame here. We can see the columns, the lower bound, upper bound. This looks nice. I want to visualize it. I always say a picture is worth 1,000 words. Let me go ahead and use a Plotly chart to visualize it. I always use Jupyter Notebooks because they create, or they give you the opportunity to create dynamic interactive plots and charts, which are very useful for zooming in and understanding the data at a more detailed level. So this just ran, and that's good. It did exactly what it's supposed to do, but I have so many data points here. I have 41. I think it starts with 0. All right, so I actually have 42 rows of data. Each one represents a column data set, and I'm looking at a lot of Q1, Q3, IQRs, right? Interquartile range. And it's a little bit overwhelming. I would say this is too much information. Most of these you can see if you mouse over. I like how these are interactive, and you have the pop-up bubble. I think it's called a tooltip or something like that. But it shows you the details here, but it's too much information. So I'm going to take only the top 10. I'm going to get the N largest. N is the number, right? Short for number. This is the summary data frame. I want the 10 largest IQRs because 42 is just too much. Okay, so let me print the columns here, and then based on those columns, I'm going to hit Control Enter to refresh the chart. If you notice the chart was already built, I want to refresh it just to show you that the code works. I'm not like just writing some random code and then copy and paste an image or something like that. No, like this is all dynamic and linked together and 100% working. So the first item here, the first bucket or feature that has the largest interquartile range is this right here, total credit limit. Let me see if I can zoom in just a tad on that guy. So here's the IQRs, right? And we have the Q1, the Q3, the lower, the upper. The max looks like 3.3. And this, let me refresh it just to get the other view back. Total credit limit, so 3 million, that's definitely an outlier here. So that's good to know. I want to know about that. Here's the annual joint income of 1.1 million. So that couple is doing quite well. The power couple right there. Annual income of 2.3 million. I think these are individuals. So that one person, whoever that is doing fantastic. Here's 1.6 million. But you can see that the IQR is really, zoom in here just a bit. Okay, cooperate, please. Okay, so here's the IQR. So you can see the upper and lower quartile, Q1, Q3. The lower is actually 0. So we have some people with 0 income. I'm not going to lend to that guy. This guy over here that has 2.3 million income, that looks like pretty low risk. I'd probably be interested in lending to that guy. So we do these types of analysis just to see the outliers. Is the data pretty tight, like you would see over here for paid late fees or paid interest or tax liens? I think it's tax liens. It's a little bit hard to read. Let's go back. Yeah, tax liens and number of mortgage accounts. So everything is pretty tight over here. Over here, when you're looking at the top 10, the deviations are much greater, right? That's what I want to show you there. So let's go ahead and start looking at the first machine learning model here to understand which of these independent variables, we have a bunch of independent variables from the data set that we're working with, can have a statistical impact on the dependent variable. So I'm not going to get into like all the machine learning nuances here, but I have several videos that describe what the X and Y variables represent. Essentially, the X is the independent and the Y is the dependent. So all of these independent variables should have an influence on the target variable, right? We want to understand the statistical impact of that relationship, okay? So we're importing the necessary libraries. We're looking at a gradient boosting classifier. This is a classification type of problem, right? So we're working with labeled data and we're trying to make a prediction for the loan status encoded, okay? And you'll see in just a minute what this is. We have all the normal label encoding over here. I have just put together a video earlier today about label encoding and how this works. You can check that out if you're interested. So we have to encode all of the categorical columns. Anything that is non-numeric is considered categorical. Once it's encoded as numeric, we can go ahead and feed that into the algorithm. Before it's encoded, we just can't run the algorithm. It'll crash, it'll throw an error, it'll complain, and it's going to basically just break down immediately. Right? Everything has to be encoded numerically to run these algorithms. Right? So we have the result here. We have the precision recall F1 score. And over here is the accuracy. So we see perfect precision recall and F1 score for the 0 target. So the 0 is nothing. The 1 is a flag. It means, okay, there's something here. There's some type of default. We're looking at credit card default or loan default. I don't think this is credit card data. I think it's loan data. So kind of similar, but I think this is loan data. But because this class is imbalanced, it's underrepresented. There's not too many defaults as you would expect. Like this is similar to fraud or money laundering. You would have a lot of cases where you don't have any real consequence. There's nothing going on. There's no urgency or concern, right? But sometimes there could be a default. Sometimes there could be money laundering. Sometimes there could be fraud. So we want to be aware of that and protect our financial institution from these threats and these risks, right? But since overall these incidents are going to occur much less frequency, we have an imbalanced data set and we have to handle that somehow, right? So we are going to use a SMOTE technique to oversample from the underrepresented class and undersample from the overrepresented class, right? So we're going to take more samples from the class equal to 1 and fewer samples from the class equal to 0, okay? So that's essentially what SMOTE is doing. You can go ahead and Google it if you haven't worked with that before. It's pretty interesting, actually. Let me see where SMOTE is actually coming into play. SMTE, a little bit hard to see it. Okay, yeah. So SMOTE is here, and we're using this while we are fitting the resample data. Here's the X train and and the Y train. This is the training data, which comes from here. Okay, and originally here is our X and Y variable. I'm not going to get into all the machine learning techniques because I have several other videos about that, and this video would go on and on and on for quite some time, and I think people probably wouldn't appreciate that and probably tune out eventually. So we'll stay on topic. So yeah, so this is running, and we're going to see what the ultimate outcome is. So before, remember, with the zero class, which we had many more cases, it looks like 1,989 cases, only 11 cases of defaults, right? We're looking at default data. So 11 defaults out of 2,000, right? That's what that represents. But these precision and recall numbers and F1 are pretty low. I want to handle that. That's where we're using the SMOTE technique to try to get these numbers boosted up. So now they look a lot better. 0.83, 0.45, that's still kind of low, 0.59. Still a little bit low, but we see a definite improvement. The AOC score, which is the ability of the model to learn and make predictions, is 96% accurate. So 96% of the time, the model will make accurate predictions, and it used to be 93, I think. Let me go up here again and check this out. Yeah, 93.2. So we went up about 3%. It was 93% accurate before. We got a small boost by using the SMOTE technique over here. We went from 93 to 96. So we picked up 3% more accuracy of the model, right? So it's 3% more accurate. So that is good. Let me go ahead and look at the probability of default based by loan status. So I think this is interesting too. Okay, so let's take a quick look over here and see what we've got. So if the loan is currently being repaid, the probability of default is pretty low. You can see it's 0.3, 0.5, so 3%, 5%. There is one that is a little bit concerning, 50%. That's an outlier. I would look into that a little bit more. That seems a little bit excessive. It should be pretty low, like close to 0, 0.3, 0.5. Probability of default should be essentially low. Fully paid, it's going to be almost 0 for these, although we did have an outlier right here, 7% for fully paid. There might be a data issue here. The data might not be totally clean or some inconsistency. I would expect a fully paid loan to have probability of default of 0 because it's fully paid, right? There's nothing that we'd expect back from that customer in terms of repayment. So this is a grace period. So I don't know what the grace period is here. It might be a week. I think with my bank, I think they give me like 8 days. So the grace period could be 8 days. And if you pay in the 8th day for my bank, then you're still in good standing. If you miss that, then you start to go into a late period. So this is 16 to 30 days. So at this bank, I guess they give you 15 calendar days so just over 2 weeks, right? By the 16th day, if you're late, then the probability of default jumps up a little bit. So I'm seeing 13.9, 14% there, 22%, 65% charge-off. So these are all loans that haven't been collected on. The bank just gave up. It's been outstanding too long, and they just had to write off these loans. There's only a handful. There's not too many of them, but we're not going to be able to collect on these guys right here. These are just bad apples. We shouldn't have lent to these customers, but we did, and we ate the loss, right? So this is late 31 to 120 days. So you can see how the deviations here. This is a box plot. You can see how the interquartile ranges, the upper, the lower, the median, the Q1, kind of bouncing all over the place because these could come back into a current status, which we see right here with a low risk of default. But some of these can just turn into charge-offs, and we just lost these. We just lost the money, right? And these are just bad loans. So this is kind of deviating all over the place. If you have a shorter, late 16 to 30 days, the chance of recovering this money is much higher. By the time it gets into this bucket, it could be gone. By the time it's over here, it's gone. Right? These are all write-offs. So that is a probability of default right there. There was one thing I wanted to show you. I think I missed a step over here. So here's the actual probability of default calculation, right? And that came from, Control CF, probability of default. Okay, so the model is predicting the probability of default based on these independent variables. Remember, the x is independent and the y is dependent, right? This is whether or not the loan will be repaid or not. That's the status of the loan. So this is dependent, and the model is making that prediction, and we're assigning that to a new column in the data frame called the imputed. Remember, we used KNN to impute the missing values, and this is the column name that we assigned to capture those probabilities. So here you can see loan status current for the first 5. We're looking at the head of the data frame by default. If you don't put a value in here, you can enter a parameter 110, 100, 1000, and it'll give you the number of records. By default, it goes to 5, right? So here's 2% probability of default, 1%, pretty low, right? Pretty low, based on all these features, right? So the model is looking at length of employment for employee, annual income, debt to income, annual joint income, debt to income joint, delinquency in the last 2 years, right? Based on all these features, we can calculate a probability of default, and that's what that is, right? So now we can look at the exposure at default, and the way we do this is just take the loan amount minus the balance. So this is pretty straightforward, okay? My son is 8 years old. I think even he can do this. So this is the exposure at default dollar amount, and there's 2 exposure at defaults. I'm sorry, there's just one. I'm sorry, this. Getting confused now a little bit. There's a lot of stuff going on here. We have the probability of default, right? We have the exposure at default, and basically this shows us the total amount the lender stands to lose if the borrower defaults at the point in time, right? So what's happening right now, and this is updated month to month as we collect more money from our borrowers every month. This exposure at default decreases, right? Because more of the loan is being repaid, so the risk is going down every month as more and more of the outstanding balance of the loan is being repaid. Although we're probably getting new customers, so new customers will have longer time frames to pay off their loan, right? If you have some guy that has 30-year mortgage and 15 years has been paid off, the risk is fairly low for that person to default. They've already paid 15 years on that thing. But if you just signed up a new customer for a new 30-year loan and that came on the books last month, now you have a new risk that has a higher probability of default because it's newer, right? And the exposure at default is much higher too, right? Because they just put the loan on your book of business last month. I'm just saying hypothetically. So now we're looking at the loss given default. So there's 2 ways that we can calculate this. There is a loss given default dollar amount and loss given default percentage amount. So let me see. I don't know. Did I refresh out? 29, 30. Yeah. So here's 30. You see how these increment 29 is here. Here's 30. And if you look at this is 14. So you can tell that this cell hasn't been refreshed. So prior to have been refreshed. If you forget, just look at the number. Now it says 31, right? So that's just incrementing one by one the cells that have been refreshed when you hit Control and Enter. So let's go look at the loss given default dollar amount and the percentage. So we have the good old probability of default. We have the exposure at default dollar amount, the loss given default dollar amount, the potential sales proceeds. Right now, this is what we could sell the loan amount for times the recovery rate, right? So if we had a mortgage, the mortgage collateral would be the house. If we could sell the house that this person had that was associated with the mortgage is tied to that asset, to that property, right? So the potential sales proceeds, the recovery rate, I'm saying is 20%. Now, this is what I said initially in the video. Some of these things are really case-by-case basis. If you work in a bank that has a higher recovery rate and you're good at going out and getting most of the collateral basically recovered, then this recovery rate is going to be much higher for your bank. I think 20% is realistic. It kind of depends on the region, where you're doing your business, right? Which part of the country. Overall, historically, how successful have you been? The fidelity of the customers, or the customers usually repay the loan, and if they don't, you can still recover most of the collateral. So there's all kinds of different examples here. I think 20% in this case makes sense, but this could be kind of an arbitrary number. You kind of have to come up with that and talk to people on your team, collaborate with some other teams, maybe finance, maybe risk management, maybe the analytics team. If you have an analytics team in-house, talk to them as well, set up the meetings, and get in front of these people and say, is this a realistic number or not, right? Because it will make a big difference, okay? So based on all of these, we can see the loss given default percentage is 0, and that's because we truncate this at 0. We can't have an LGD negative, right? That doesn't make any sense. Some of these numbers just can't be negative. It doesn't make sense for the business to have that. So we could truncate that using 0 as a floor. Otherwise, use the actual number for the LGD if that number is positive. And then again, all of these are current status, right? So an LGD of 0% or 0%, that makes sense. That makes sense to me, right? Now we can calculate the expected loss. So the expected loss, wait, let me shut this down. The expected loss is the result of multiplying probability of default times the exposure at default times the loss given default. And the product of all of these will give you the expected loss on the loan. So let me go ahead and do that. So this is going off to the right. Expected loss is 0, right? Because of this right here. Multiplying 0 by 0, we're going to have 0, right? So we expect loss of 0 because the LGD percent was 0. So that's interesting. In this case, we're actually, I Googled this, so this is the right way to do it. You have an LGD dollar amount, but for the expected loss, you really want to use LGD percentage amount. That's my understanding when I Googled this, and I did this years and years ago, so I think that makes sense. If not, somebody can correct me, but I think this is done correctly. If you did somehow use the LGD dollar, you would just update this right here, over here, and run the analysis. I don't think that makes sense. I don't think that's the right way to do it. I think this is a correct calculation. So the expected loss shows you the average anticipated loss for any lender due to the credit risk, right? And again, these risks are pretty low. You can see probably a default of less than 1%, less than 1%, 1, 2%. These are pretty tiny, right? So let's look at something a little more interesting because all these expected losses are 0. Let's filter out, the filter string would be late 16 to 30 days. So this is in the bucket where the payments are coming in a little bit late, 16 to 30 days. We're going to focus just on the subgroup. And you can see there's 38 records here, right? When we looked at the whole thing before, that even get the size of the date frame, I don't see it. Okay, it doesn't matter, but this is much smaller. Actually, let me go back and do this. Okay, let me redo this. Sorry. It's curious now. So the original data frame, 10,000 records, right? And we have 62 columns. Now, when we look just at this subset, it's actually 38 columns and the same number of, 38 rows and the same number of columns, right? It's always row, column. So we have 38 rows that are in this bucket, late 16 to 30 days. And let's see what the numerics look like over here. So probability default a little bit higher. Now instead of 0.1, we're seeing 0.9. These are lows. This is 0.1, 0.1. But still expected loss is 0. So I think this is pretty safe. We have some good business on the book. I'm not too concerned about this. Now we have 66 rows. So we went from 38 to 62. Now this is a new bucket we're looking at. We're filtering based on late 31 to 120 days. Now this is more risky, right? So the scenario has a higher probability of default, 0.7, so 70%, 95%. That doesn't look good at all. 86, 89, 21. Just because these guys are up to 120 days late, but still the loss given default is still 0 because the LGD percentage is still 0. So the expected loss should still be 0. But if we do have an exposure, this is the dollar amount right here. So we still have some exposure, but it's only, look at $278. It's not a big deal. $142, $239, right? So pretty small amount, even if the default did occur. This is charge off. So these loans are basically skunks, right? These are dead. We're going to take a hit. We're going to eat it here. We only have 7, so it's not too bad. Of 10,000 overall, I think our analysis is pretty solid. Probability of default 81, 47%, 76, 99%. Okay, I wouldn't want to be that guy. And 51%. But now we do get an LGD percentage of 8, so we're getting some expected losses here. Just under 5,000, just over 6,000, 1,800, 15,000. Okay, so we'll eat that one, and 8,185, but not big numbers, guys. So I think overall the analysis is solid. The way the business is being run right now is pretty tight, pretty crisp. The expected losses on this whole portfolio of 10,000 loans is actually pretty small relative to the book of business, right? So calculating PD, LGD, and EAD provides a comprehensive view of credit risk, right? We want to make as many loans as possible. If we're making no loans, we have no business. We're not going to be around too long, right? But we can't loan to every single Tom, Dick, and Harry that comes up to us. We want to be discreet or discretionary about who we loan to, right? But we want to avoid the bad loans, right? So we want to make as many loans as we possibly can without loaning to the bad customers that potentially are not going to pay us off, right? So this analysis helps us do exactly that. So overall, we manage risk for a variety of reasons, right? Safeguarding financial stability and enhancing profitability, complying with regulatory requirements, right? There's a lot of regulatory compliance in the banking sector, protecting depositors and maintaining customer confidence, right? If we had a whole bunch of bad loans we had to write off, that's probably going to be picked up by the newspaper. Your bank is going to be on the front page of the newspaper, and not for good reason. You don't want that kind of publicity, right? There could be a run on the bank, and as we all know, banks lend out about 90% of the reserves that they have. They only keep 10% at the bank. So if there's a run, you could see the bank go out of business real quick. We saw that several times since 2008, but that's been going on for hundreds of years, right? If everybody goes to the bank and withdraws their money all at once, that bank is done, right? So we want to maintain customer confidence, ensure liquidity and operational continuity, support information making decisions, strategic planning, data-driven insights. We want to make intelligent decisions to reduce systematic risks and achieve economic stability. So that's it. This is the data source. I showed you that before, and this is the end of the teaching lesson. So hopefully you guys learned something new. I definitely learned something when I was putting together these scripts. Hopefully it was time well spent for you, and this was an educational experience. So that's pretty much it. Thanks so much for your time. As always, I'm going to log off now. Enjoy the rest of your day. I will do the same. Thank you. Bye.